Hey everyone, and welcome. Today we're going to dive into a really core concept in computer science, how we can build a queue data structure from scratch using a linked list. And we'll be doing it all in C++. So let's jump right in.
So, have you ever thought about this? I mean, we all get what it means to wait in line, right? But how in the world do you get a computer to understand that same concept, to process things in a fair, orderly way? Well, that is exactly what we're going to unpack.
You know, the easiest way to wrap your head around a queue is to think about something we've all done a million times, waiting in line for tickets. It's simple, right? The first person to show up is the first person to get served. It's just intuitive. First come, first served.
And that right there, that's the heart of it. It's a principle called FIFO, which stands for first in, first out. It's a guarantee. Whatever you put into the line first is absolutely going to be the first thing that comes out. It's the simple rule that keeps everything fair, whether you're at the movies or running code on a processor.
Okay, so we've got that idea down, right? First one in is the first one out. Now let's jump from the ticket line over to the command line and get a bit more formal about what a queue actually is in the world of data structures.
So, in computer science terms, a queue is what we call a linear data structure. It's just a line of things. But here's the catch, the thing that makes it a queue. You can only add new things to one specific end, which we call the rear, and you can only take things away from the other end, called the front. That two-ended system is what locks in that FIFO rule we just talked about.
Let's look at it like this. Imagine these are tasks in a line. The number 10 is at the front. It got here first, so it's going to be the first to leave. If a new task, say the number 40, wanted to join, it would have to get in line all the way at the back, at the rear, behind 30. It's a super simple but really powerful setup.
All right, so you could build a queue a couple of different ways, but for this explainer, we're going to focus on using a linked list. And the big question is, why? What makes a linked list such a good tool for this particular job?
Well, it really comes down to a few huge advantages. First off, linked lists are dynamic. They can get as big or as small as they need to be. You're not stuck with a fixed size like you might be with an array, so you don't have to guess how much space you'll need. You won't run out of room until your computer is literally out of memory. And, this is the big one, adding an item to the back and removing one from the front are both super efficient.
Okay, enough theory. Let's get our hands dirty and actually see what this looks like in C++ code. We're going to build our queue piece by piece from the ground up. Every single linked list is built out of this one thing, the node. It's our Lego brick. If you look at the C++ code for our node struct, it's got two jobs. First, int data. That's where we store the actual information, the value. And second, node pointer next. That's a pointer. You can just think of it as an arrow that points to the very next node in the line. It's how everyone in the queue knows who's directly behind them.
Okay, so if each node is a person in line, we need some way to know who's at the very front and who just got to the very back. That's where two special pointers come in, front and rear. The front pointer always points to the first node, and the rear pointer always points to the last one. Think of them as the bouncers who know exactly where the line starts and ends.
So, let's talk about adding someone to the line. In our world, that's called enqueue. This function is all about adding a new node to the back of the queue. You can see in the code, it makes a new node, it checks to see if the queue is empty, and then it correctly hooks that new node onto the end of the chain.
So, what's actually happening here? Step 1, we create a shiny new node. If the line was totally empty before, then this new node is both the front and the rear. But if there are already people in line, we just tell the person who's currently last to point to our new guy. And then, the final step, we move our rear pointer to say, hey, you're the new end of the line now. Simple as that. Okay, so we've added people to the line. What about serving them? That's dequeue. This function's job is to remove the person at the very front. You can see the code checks if there's anyone to serve, and then it's very careful about how it rewires those pointers before letting the old node go.
So here's the play-by-play for dequeue. First, we make a note of who's currently at the front. Then, we tell our main front pointer to move up one spot, to the next person in line. Once that's done, it's safe to remove the old front node. And there's one really important edge case. What if we just served the very last person? Well, now the line is empty, so we have to make sure our rear pointer is also set to null.
Okay, we've got our building blocks, the node, our pointers, and our two main functions enqueue and dequeue. Now for the fun part. Let's put it all together and see our queue actually work. So check this out.
In our main function, we start with an empty queue, obviously. Then boom, we enqueue 10, then 20, then 30. When we display the queue, there they are, in that exact order. Then we call dequeue. That removes the 10, and when we display it a second time, you can see that 20 has now moved up to the front of the line. It just works.
And this is the real kicker. This is why this data structure is so cool. Both adding an item and removing an item take what we call O of 1, or constant time. All that means is it doesn't matter if you have 10 things in your queue or 10 million things in your queue. The time it takes is always the same. Because all we're ever doing is just tweaking 1 or 2 pointers. It's incredibly fast.
And because they're so ridiculously efficient, you start to see queues everywhere once you know what to look for. Your computer's operating system is using a queue right now to decide which program gets to run next. When you send 5 documents to the printer, they sit in a print queue. It's a key part of powerful algorithms like breadth-first search. It's even what keeps your Netflix stream playing smoothly without constant buffering.
So I want to leave you with this thought as we wrap up. Now that you get the whole first in, first out idea and you see how it's built, start looking around. Where else in your digital life do you see this elegant, orderly system of waiting in line? At work. Think about it. Thanks for watching.